optimization tool, and now here are the problems that can be solved with that tool. But nevertheless, I mean, this is not going to exhaust all the possibilities. So I think well, I'm not supposed to comment on this until the competition is over at 6 p.m. But I'll say that the more the more tools you know, and especially if you know partial differential equations, then you can model kind of waves, vibrations, and okay, so the company is called COMAP. And if you look at the contests, it's called MCM, Math Contest in Modeling. And these are the contest problems this year. So, and again, it's still ongoing. So there's one problem of this sweet spot of a baseball. Second problem has to do with some sort of profiling, geographically profiling the location of a criminal based on the crimes that he or she committed. And the last one has to do with this garbage patch in the Pacific. So it's kind of interesting. Usually the description of this kind of interdisciplinary problems take 20 pages. So lots of data, lots of things to look at, and try to come up with a model that explains. And I think they also refer to a paper here. So, but what I want to say is that you can look at previous contests here if you're just kind of curious, and you will see lots of. A wide variety. I think last year there was one that had to design a traffic circle, which in the United States is more of a curiosity, right? But in other parts of the world is really crucial that you have efficient traffic circles. Energy, cell phones. I think that's a problem that UCCS team chose last year. It had to design a cell from scratch. Like if you have a whole new country that you have to build the infrastructure, do you build landlines, or do you just rely on cell phones? Very open-ended questions. There's no wrong answer, and in fact, nobody has been graded on those reports saying this is wrong. But a lot of the papers are kind of disregarded because it says presentation is not appealing. There's no sequence of thoughts, right? Or the model is not built well, or something like that, right? So it's anyway. So we could. People that have good experience with computational tools usually have an edge on this competition. So it's as usual, in real modeling, it's an essential part. So you can take a look at this if you want. Okay. So let me come back to any questions before we start? Any questions about homework that I turned in? Yeah. No, thank you for. So I pushed it back to. Let's see. To next Monday. So there are 3 problems. It shouldn't take you till Monday, but I figured if you need a little bit of extra time. So I'm sorry. So The homework is due Monday. I'll tell you one thing about Chapter 4 and Chapter 5 are pretty much can be read lumped together. So, these three problems, I would say if you finish them after Wednesday, maybe we talk more on Wednesday, then you can start working on Chapter 5. And on Wednesday we should start talking about Chapter 5 as well. Right now I left it the same, yeah. Okay. So today I'd like to talk about two examples of dynamical systems. We started talking about last time a little bit, so let me remind you what dynamical systems models are. I just want to copy another. So I have two codes here, two new codes. One talking about a continuous system, and the other talking about a discrete system. So we'll see what the differences are. Okay. Please. Okay, so I'm going to start with talking about, give you an example of a 2D. Well, 1D we saw last time. So I said 1D model would be a logistic model that usually comes from population growth and it says that if I have x as a function of t, it's monitoring the population at time t. Then, let's see, so I'm going to put here in parentheses the rate of change, the growth rate of the population has this expression. So this is Rx plus or minus, excuse me, minus R over K x squared, right? So this is just a constant. Think about it as just a positive constant A, right? So this, every time you build a model, you have to kind of take into account certain effects. In a population growth, there's an intrinsic growth rate, so that's assuming that the bigger the population, the faster it grows, and that applies to I don't know, bacteria population or things that so individuals that don't kind of compete with themselves. It's just kind of unrestricted growth. So this is an intrinsic growth rate. So that's the reason for that is if you only look at that effect, so you ignore every other effect, then what you see here is you see an exponential growth. Right? And R plays the role of that growth rate. Yeah? So R is the, if you want a sort of a, well, is the ratio between the growth rate and the current population. Okay? So that's called the intrinsic growth rate. But if you have other effects, for instance, if you have a limited environment in which your population kind of lives and thrives, and you take into account competition between between the same individuals of the same species, then there is simplest model is to introduce a term, quadratic term, that comes from product of x with x, right? And a constant in front of it, meaning that the competition kind of inhibits the growth, right? So the growth rate is decreased at a rate proportional to the square of the population size, right? So again, the higher the population, the faster the bigger the effect, the negative effect on the growth. Okay. Again, this is not the only one, and we'll see other models, but this is considered to be sort of the next simplest from exponential growth. Okay, so this would be just exponential model. All right, and why do we prefer to write it in this form rather than in this form, which is probably, again, more intuitive? The reason we write it in this form is that if you look at the steady states of this population, and we say, what would the population have to be initially so that it stays at that value forever? So that would be a constant solution to this equation. And remember, we said that constant solution means the right-hand side has to be equal to 0. So having it as a product is just convenient. Okay? Because you can see the right-hand side is 0 if x is 0 or if x equals k. Right? So we saw that in the direction field. We saw that zero and k were the two steady states. So this is steady state if the right-hand side at x star is 0, right? So for logistic model, x1 minus x over k is 0 gives you those two solutions, x star equals 0 and x star equals k. Okay. Not only that, but we saw from the direction field, we saw that, and also from the solutions. Remember, we kind of computed the solutions. We could compute the solutions explicitly, and we saw that over time, so for x of 0, so that's the initial condition, is positive, then x of t approaches this value k as t goes to infinity. When if the initial condition was not 0 but was negative, then you had negative infinity. Yeah. So this value k has a meaning of, well, in the population dynamics, k is called maximum sustainable population. So It's just saying that that environment, in that environment, so with those two effects, a population of size less than this value will thrive, but will kind of approach that value. And a population that starts, it's overcrowded, with a value that's greater than that particular number, it's going to decrease. It's going to the competition is stronger than the actual intrinsic growth, so there's going to be a decrease, and again to that value, right? So sustainable, and if you start at that value, you're going to stay at that value. Okay. All right. So, yeah.
What is that last line saying? Population dynamics?
Yeah, population dynamics, right? Yeah. So, in the example that we're going to be talking about the next few, I guess, lectures, we're going to see more of the population dynamics than economics, like manufacturing, right? So you'll see this word, this term quite a bit, sustainable population, and that kind of means there's a logistic model underneath, right? So here's an example in 2D. Competing species model. So I'll write down the system, and then we'll see where it might come from. So I have two variables that I'm tracking over time, and those are population of two different species. So this is population of species 1. I'm going to use blue and fin whales, blue whales versus fin whales. So let's say population of blue whales is x1, and population of fin whales is x2 at time t, at a given time t. Now, obviously, these numbers are integer, right? So there's not like a half of a whale. So obviously, as time evolves, more whales are born, and some die. So this is not going to be a continuous variable, right? But the assumption here is that we're going to be talking about a large period, like hundreds of years, right? Thousands of years, and then a large population, right? So there's going to be some sort of an approximation to say that over that large period of time, these variables can be considered to be continuous. So when we talk about a rate of change, we can talk about a derivative. And not only that, but we can think about each population has sort of a logistic growth. Right? And again, remember, these are kind of the simplest possible. Well, I guess the simplest would be to consider exponential growth. Okay? But for large animals, there's always going to be some sort of overcrowding effect. So exponential growth works for really tiny individuals, so population of bacteria or something. When we're talking about large-sized animals, then we have to have some sort of maximum sustainable population. So these are sort of the simplest two models, right? The simplest model for population growth. And now, in addition to that, we're going to introduce a competition effect. So this term would be sort of competition between individuals of the same species. But now, if they both coexist, then there's going to be some term that inhibits the growth of each population. So that is a negative term to the rate of growth, right? And it's proportional to the number of interactions between the two species. So the product between x1 and x2. Yeah.
So does this simple model allow for predators, or is this?
No, this is competition. Yes, still.
Competition.
Yeah.
Between two similar species.
Right. We're going to talk about predator, next, I guess. But predator prey. So this would be a different model. I mean, a different setup. You would have a system where there's some sort of intrinsic growth, right? In absence of the other species, then the predator would be some sort of a positive term because prey helps predator grow, right? And the prey would be a negative term because predator kill prey. So it's just kind of a different sign here. So it's not. I mean, setting it up is not different, but the dynamics could be quite different. Okay, so here we're just going to use this simplistic model, and even the fact that we use same constant, can be debated, right? So the constant of proportionality here for this competition term doesn't have to be the same. It could have different ones, right? But when you think about putting this, matching this with a real system, like let's say in the Pacific, right? I think that's it's quite a big issue in marine biology, in figuring out how much fish is in the ocean, right? Which species are being endangered? Should we stop? What do we do? I mean, should we repopulate and so forth? So just fitting such models with the real stuff is extremely difficult because you don't know. You know nothing about this intrinsic growth rate. You know very little about the maximum sustaining population of each population, right? You know even little less about what the presence of one species does on the other, right? So we really would need data that spans, hundreds of years to get good fits for these things, right? And we don't have that data. That data, I think, even now it's hard to collect data, but whatever data is available for the last, 50, 100 years at most. Unless the Eskimos were collecting data in their own way, and we just don't know how to interpret that. So again, what's most important thing is competing species is the fact that this term is negative, right? So we put negative and we put alpha to be positive. Okay, so what do we do with this? Well, first thing that we want to do is we'd like to understand. So the goal is to understand the dynamics of the two species depending on their initial populations levels, if you want. So x1 of 0 is x1 0, x2 of 0 is x2 0. Okay, and other things we'd like to find out steady states. which in this case would be called or equilibrium, and these are called coexistence states if x1 star, so I'm going to use this x1 x star to be x1 star x2 star, if these things are positive. So very soon we're going to be looking at this phase plane in which we plot x1 versus x2, right? And we're going to be tracking initial conditions. I mean, we're going to start with an initial condition here, right? So initial population is this much for x1 and this much for x2, and we're going to follow that trajectory. And in that plane, there's going to be special points, the steady states, for which if I start here, I'm going to stay here, right, for all times. And they're called coexistence because if there's a value here, right, if there's an equilibrium where both x1 and x2 are positive, this means that if you start with those two values, they're going to stay forever, right? So we'll see an example in a minute, but again, there could be a coexistent equilibrium here, so this would be x star, and there could be other initial conditions that go to this, right? This would qualify this equilibrium steady state to be, not only coexistence equilibrium, but it would be a stable coexistence equilibrium. Right? It says that I can be, I don't know for sure the initial population what it is, but if it's in the ballpark of this steady state, then as time evolves, it's going to just get even closer to those values, right? Now, there's actually a possibility that you have something that's coexistence equilibrium, but it's unstable. That is, well, we'll see examples of that. Okay, but keep in mind about this being positive. It's important to be positive. If you have a stable or a steady state or an equilibrium that's for which x2 is 0, what does that mean? And you have an it could be stable or unstable.
The population ceased to exist.
Right. It says that the population x2 is going to go to 0, right? So that's not coexistence. But it's still a steady state, yeah. So coexistence only if both are strictly positive. Okay, so we're going to look at the stability. So a stable equilibrium is such that initial conditions that are close to that equilibrium approach that equilibrium. The solution starting at those initial conditions approach. So if x of t approaches x star for x of 0, which is x0, is close to x star. Okay, and we're going to define basically unstable is an equilibrium that's not stable. Okay, and we'll see how that can happen. All right, so let's kind of be a little bit more specific for this example, for this coexistence equilibrium. So let's start with a steady state first. A steady state analysis. I guess that would be sort of the first thing to look at. So, in general, let's say I have a system of two equations, but it could be in general, n equations and n unknowns. So if I have these two equations, then an equilibrium x star solves, so let's call it x. Notice that I'm using capitals, capital X to indicate it's a vector of coordinates x1, x2. So this solves the system f1 of x1, x2 equals 0. So where you set the right-hand sides equal to 0 simultaneously. So I'm going to emphasize this. It's a system saying we have to solve both f, the first right-hand side equal to 0, and the second right-hand side equal to 0. Okay? Okay? So in the whale problem, in our whale problem, coexistence modeling, excuse me, not coexistence, competing species model. What's the right-hand side? What's the left-hand side? Or the right-hand side. So I have dx1 dt equals r1 x1 1 minus x1 over k1 minus alpha x1 x2. And I have to set this equal to 0, and dx2 dt is r2 x2 1 minus x2 over k2 minus alpha x1 x2. So I have to set both equal to 0. So let me use two different colors here. So I'm going to set first one equal to 0 in red, and the second one equal to 0 in blue. And I want to show you this in the plane x1, x2. I want to pinpoint the locations where both are equal to 0. Okay. So here's how we do it. We're going to take the first equation and we're going to graph it, or find the points x1, x2 for which the first equation is satisfied. Right? We're going to use red to indicate that. And let's see. How do you solve the first equation? Well, you see x1 is a common factor, so you see that I can factor x1. I get r1 1 minus x1 over k1 minus alpha x2 equals 0. Right? And this leads to either x1 equals 0 or r1 minus r1 1 minus x1 over k1 minus alpha x2 equals 0. Right? So what's the first one? x1 equals 0 is the x2 axis. Okay? So any point on the x2 axis makes the red equation satisfied, right? And the second equation is just a linear equation of x1, x2. So the graph, it's a line, right? Now, how this line is, we don't know until we figure out the exact values for R1, K1, and alpha. But it's something like, let's say something like this, right? So this is x1 equals 0, and this is r1, 1 minus x1 over k1 minus alpha, x2 equals 0. Okay. And you do the same thing with the other one. So x2, so at this point, this collection of points, we call it to be the null line. So let me write this word here. So this is called the null line. Corresponding to the first variable. So x1 null line if you want, right? So this is going to be the red null line and the blue null line. Blue is a blue whale, so I don't want to. Let's use green instead. The green null line is similar, right? So again, unless we know the exact values of these constants, we cannot plot, very correctly. But at least these are lines, and we know the x-axis and so forth. So the green null line would be the x2 equals 0, and the other one is something like this, right? Okay, so the question is, what are the equilibria? If you know these null lines, the equilibria will be always where the null lines intersect, right? Well, it's where the null lines of different colors intersect. For instance, where the green line meets the green line here, that point would not be an equilibrium, right? Because it has to be a point that leaves on both null lines of different colors. So that's why it's useful to use different colors, because you can see where those equilibria will appear. And of course, on paper, this says the steady states are x1 equals 0, x2 equals 0. That's one of them, right? What's the other? Well, could be x1 equals 0 and this thing equals 0, right? But if x1 equals 0 and this one has to be 0, well, x1 is 0. So this thing has to be 0, so x2 has to be equal to k2. That means there's no species 1. Well, the equilibrium has to be basically where the species 2 is the maximum sustainable population. And the same, if x2 is 0, then x1 has to be k1. So this is 1, 2, 3, and the fourth is hopefully where coexistence occurs, right? So this would be solving the r1, 1 minus x1 over k1, minus alpha x2 equals 0, r2, 1 minus x2 over k2, minus alpha x1 equals 0. Okay? And it's a system of two equations with two unknowns. So this is a linear system, actually. So you could actually do it even by hand if the constants would be nice. Okay? And it's not guaranteed that this is always going to be a coexistence equilibrium, because it could actually very well be you have one positive and one negative value, right? I mean, you've solved linear systems before, 2 by 2, and you've gotten positive and, sometimes, I mean, they don't have to be positive numbers, right? the solution of a system of two equations and two unknowns. Okay, so let's look at the Wales code here, and the numbers will not be very pretty. For instance, alpha is 10 to negative 7. That's pretty much a guess. But the magnitude of it, being so small, it says that, the two species really don't bother each other too much. It's not like one is a predator. Well, no. It just says that the competition between the two species is not affecting the growth unless the size of the population would be, of 10 to the, the product would be 10 to the 7 and so forth, right? Let's see. The intrinsic growth rate for the blue whales population is 5%. And 8% is for the fin whales. So I don't know which one's actually bigger size animal, but possibly the blue whales is larger, right? The smaller the animal, the higher the intrinsic growth rate would be. Also, the maximum sustained population is 150,000 for blue whales and 400,000 for fin whales, right? Has to say something about the size, I guess. And then, right, so this is the right-hand side of that system. All right. So, again, if you use MATLAB, then to find the steady states, you just simply say, close your eyes, and say, solve the system f1 equals 0, f2 equals 0, and hope that you get everything. Right? Remember, you work in symbolic. Well, if you work in symbolic world, then you always have to be wary a little bit of the outputs. So right now I'm just going to define the right-hand sides, and I'm going to solve it. Okay? And because the system was even, you could do it by hand if you have the time, you can see that you really get the 4 points. Right? The nothing, nothing, maximum sustained population, 0, 0, maximum sustained population, and then the coexistence equilibrium. Okay, so that would be the steady state analysis if you want. Okay, it's pretty basic. But the very next thing is to say, well, if I start with an initial population that's not any of those 4 values, how is the population of the two species going to evolve in time? Right? So you have to solve that system of differential equations. And I mentioned last time a little bit about this. So this would be the steady states. Now the phase portrait. Well, first of all, let's start with the direction field. So direction field of a dynamical system is really the dynamical system can be written as a one single equation, well, matrix equation if you want, or vector equation. So we're going to put the so x is x1, x2, right? And this is a function of time. And f of x is, it's also a vector f1, if you want, of x, and f2 of x. Right? The right-hand sides. So the phase plane is the x1, x2 plane. And what is the direction field in this plane? x1 and x2 have to be positive, so we only care about the first quadrant here. So there's going to be basically, just as an illustration here, every point in the plane is going to be associated with a direction, and the direction is, so what's you know, if I pick this point and I want to compute the solution of that system and display it here, then I can do this. I can compute. I can measure f1, f2, and then I'm going to get that slope, right? Because remember, dx1 dt is f1, dx2 dt is f2. So unless it's one of them is 0, let's say none of them is 0, both are not 0, then you could get that dx2 over dx1 is what? Well, it's the ratio of the derivative of dx of x2 with respect to t, and derivative of x1 with respect to t, right? So that's be f2 over f1. So there'd be, if I were to plot x2 versus x1 at this point, then the slope of that curve, or of the tangent line to that curve, would be the ratio of f2 over f1, right? So that's why every time you direction field is displayed like this. Okay, you measure f2 and f1. Now, we'll see what happens when you happen to be on a null line. So, for instance, if f2 happens to be 0 at a point, so this means you're on on the green null line. This means that the slope, the direction is going to be horizontal, right? When you are on the null line where f1 equals 0, the direction is always going to be vertical. Okay, so let's see this. Okay, and I have to say one word about how MATLAB actually displays this vector field. So, of course, we're going to sometimes use p-plane just for convenience, but there's kind of a funny syntax here. For instance, if I want to, well, obviously you cannot display direction field for every single point in the plane. So, if you choose you have to choose the window size. So x1, say between 0 and 900,000, x2 between 0 and 600,000. The window size has to capture the steady states, right? If you want to see the whole picture. And then I choose 10 points to to display 10 points by 10 points. So a grid of 100 points. I'm going to see 100 directions. And then unfortunately, well, I think the easiest one would be to kind of code once again the right-hand sides, to write the right-hand sides, and preface that by this command meshgrid. So meshgrid basically just computes those 100 points, x1 and x2, and then here it just computes the two directions, the f1 and f2, and the main command is quiver. Quiver is for for basically plotting the arrows, and you have to display x1, x2, and f1 and f2. Okay, and then you just kind of put the axis here. So let's see what this does. Okay, so these are 100 points and the arrows. Now, this is not perfect. Why is it not perfect? Well, first of all, the length of the arrows don't necessarily match with the exact values of the right? I mean, I think if you'd like to display exactly the size of each arrow, I think it will look messy. I think you have to put like I think 0. Let's see if 0 works. Yeah, see? Maybe I should clear the figure and redo it here. So this quiver, you can force it to display the vectors with their exact lengths, but then you don't see much. Right? It could get really messy, or you could ask it to just rescale. So this is a kind of a rescale, automatic rescale. So you just see the directions, you don't see the magnitudes. Okay, but anyway, this is the direction field. Okay, and now the next thing to do is, as I said, to identify the steady state by drawing the null clients. So for null clients, it's fairly easy. Just say solve f1 equal to 0 and plot it. So, and then hold on. And do the same for the second one. And I don't think I've used different colors, but you can certainly use different colors. But these are, and again, it doesn't plot the like x1 equals 0, x2 equals 0. Or maybe it did, but it doesn't show here. Right? So from this, it's hard to see actually more than just the equilibria, right? You see the equilibrium? I mean, we knew this is 150,000. We knew that was a 400,000, right? And we can figure out, we can ask the computer to, well, actually it did plot, right? It did compute the steady state, the coexistent equilibrium. But I mean, it's hard to say what happens with an initial condition that's not one of those 4 points, right? So I make a comment here that if you want to see what happens, there are two options. One is to code here, for instance, one of the OD solvers, and just give the initial condition. Say what happens if I start at 400, I don't know, 200,000 and 500,000, right? Then it's going to compute that by solving the system of equations, but it's not too pleasant. So that's why p-plane is actually much better here. All right. And when we do p-plane, what we see is we see the actual solution starting close to that coexistence equilibrium, actually approach that equilibrium as t goes to infinity. Right? So we call that to be a stable equilibrium. Okay. All right. So I'm going to switch to p-plane in a second. But while I'm here, there are issues of sensitivity to the parameters. Remember, those values of the parameters by no means are set in stone. I mean, certainly 10 to negative 7 is not by far anything that you should bet on. So you can do sensitivity to this parameter alpha, for instance, and you won't be able to do anything like a direction field. But one thing you can do is you can ask the computer to try to find the steady state for as a function of that parameter. And you can see, for instance, with respect to alpha, that's what it is. What do you do with this? Probably the best way is to plot, because otherwise it doesn't register what, whoops. I skipped. I'm sorry. I skipped a cell. Okay. And yeah. And then what do you do with those a coexistent equilibrium with respect to the parameter alpha. Well, so what does it mean, sensitivity to that? I mean, of course, a numerical value, ratio of relative changes could be something to do, but I think it's more reasonable to ask, for what value of alpha there's going to be no more coexistence. So here you see when I solve x1 of alpha, x1 is a function of alpha, I solve it equal to 0. What am I doing? For x2, alpha equals 0. Right, so I get a value for alpha. What is that? Right, this value of alpha.
You can then plug in like 0 for x2 and so on for value of alpha is 0.
No, so this value I obtain it by taking that expression that I found for x1 or x2, or let's say x1, and I set it equal to 0.
Isn't that the value that's going to drive x2 to 0?
Right, so this means that for this value, the fourth equilibrium is going to be kind of stuck on an axis, right? Being on an axis means it's no longer a coexistence, right? So this value, there's no more coexistence. This is the value where x1, the bluefin, the blue whales, would be extinct, right? This would be the value for which the fin whales would be extinct. It's probably easiest if you do this graph. But again, this is by far just the only way to do it. So here I just plot x1 as a function of alpha and x2 as a function of alpha. And you should really use different colors. I'm sorry. As a versus alpha, right? So what this says is, and you can see for what values of alpha both are above 0. That's what it means coexistence. So it's for these values of alpha and for these values of alpha. So it has to be either too few, small competition, smaller than this value or larger than this value, right? And I think just fancy way of doing this by identifying the points where it's actually right. So it's saying that for alpha greater than 5.3 10 to negative 7, the coexistence, there's going to be a coexistence equilibrium, right? And for values for alpha less than this, it's going to be a coexistence equilibrium. I mean, in essence, what this is actually solving a system of two inequalities. Okay, but not by hand, by using a computer. Okay. Any questions on this? One advice is don't necessarily take this as the way to represent your, solution or your report. As far as the graphical, okay. This is just one way of doing it. In different problems, it may actually look different, right? But sensitivity to a parameter is really about, at what point, is that conclusion going to be different? So, our conclusion was that if I have 10 to negative 7, then there is a coexistence, right? Well, if alpha is not that, but just slightly more, then there is no more coexistence equilibrium, right? So that would be sort of the sensitivity. Okay, so C Wales code. So this would be stability done with p-plane. I think right now it's p-plane 8. Okay, so let me oops, I thought I had that on. Didn't I show you people? I showed you p-plane last time a little bit, right? So somehow it's not on this machine. So let me put it back on here. Oops. You don't want to modify this code at all. I just want to call it. Okay, so if you look in the gallery here, there is, I think there is a competing species model already. So, okay, it's using different values, so I'm going to just show you with these values, but you can just change these numbers, right? And call it, instead of x, y, call it x1, x2, and so forth. Okay, but you can see ways of doing this. For instance, you can find, you can show the null line. It just shows them to you. Okay, it's not perfect. It's not going to be perfect. Sometimes it's kind of, you can see this here is like an artifact, right? So it's not a perfect graphical tool, but you can actually, let's see, you can find equilibrium points. I think I showed you last time. So you can just pinpoint, and it's gonna, you have to do it one at a time, and you have to be close to, whoops, oh yeah, that's a good example here. Is this an equilibrium point? No, because this is same color lines, right? So this is not a intersection of two null lines, right? So I was hitting that, and it wasn't giving me because that was, but this one is, right? Okay, and let me just say this. So here, the eigenvalues and eigenvectors, we're going to basically in chapter 5, we're going to link this eigenvalues of the Jacobian metrics, the sign of these eigenvalues with the stability properties. So for instance, the fact that both of these are negative says that that equilibrium is stable, right? And it's called a sink because everything is kind of sucked into that point. We didn't really watch what this was, but you can see one is positive, one is negative. So this is not a stable equilibrium, right? So it's not a sink. Yeah. Well, it's a saddle point. Basically, it says there's only one direction in which is stable, and on all other direction is actually going to be unstable. It looks like a saddle. So let's just see a few solutions here. You can see it here. Okay, now let me say this is not the whale, right? For the whale problem, you had different values there. You had to put the different values, and then what you would see, you would actually see a sink. You would see a stable equilibrium here, the coexistent equilibrium, right? But again, the tool is the same. Okay? And that's pretty wonderful, right? You solve a system by just clicking. But this phase portrait, as it's called, contains null lines, several solution curves, right? The equilibrium. So you can read a lot of things out of it. You can read the stability properties of the equilibrium. You can also see what happens with certain initial conditions by doing a keyboard input. So you can say initial value is, well, let me clear this. So you can start with an initial condition that, I don't know, maybe in this case would be 0.4 and 0.6. and it wasn't too great because it went forward and backward in time. So you would need to see the you need to see what? Oh, you need to see the arrows here to see which direction it goes, right? Or else you could do. Let me erase again. You could do solution direction. It could be just forward in time. It's just a nice graphical interface, so you don't have to code any of this. But and then when you compute it, you see, it starts at that point and it goes towards that equilibrium, right? Meaning this species goes extinct, right? Okay. So we'll talk about discrete systems on Wednesday. But let me just say that for discrete systems, the only difference is that typically it's not a rate of change as a function of the current state, but it's some sort of a discrete change. So it's not instantaneous change, it's like a discrete change. So it's a change in the values over some fixed time. For instance, I don't know, a day or a year. Right? It could be a whale population model, but you know how the population changes once a year, right? Based on the current state, you know what's going to be a year from today. So if it were the same direction field, what you would see is actually, you would just see, starting with the initial condition. Whoops, that's a bad example here, but let me just display that. So it has to do with, in this case, it's a docking problem, which is kind of interesting. But just to show you so imagine that you would have a direction field that's like this. If it's a continuous system, you would fit curves that actually are tangent to this directions, right? Whereas if it is discrete, let's say over 1 year, let's imagine it's a whale problem, right? You would have this initial population, and then a year later it would be this based on this discrete model, right? Now, again, why this big when the arrow was this small? Well, it turns out that the arrow was this big, but this was a displayed scale down, so you can see the arrows. If you didn't scale down, you would see just a forest of arrows here, right? But this is one arrow that initiates at this point, right? Then after a year, it follows this, right? It still follows a direction field, but in a discrete fashion. And you can imagine that it's going to have different behavior, possibly. Okay? Sometimes discrete models are required because of the nature of the problem you're talking about. Sometimes continuous models are good approximations. Okay? So we're good. We have homework that's due a week from today. So, but I would get started on the two problems that are continuous, and we'll talk about discrete one on Wednesday. All right. Thanks. In other parts of the world is really crucial that you have efficient traffic circles. Energy, cell phones. I think that's a problem that UCCS team chose last year. It had to design a cell from scratch. Like if you have a whole new country that you have to build the infrastructure, do you build landlines or do you just rely on cell phones? very open-ended questions. There's no wrong answer, and in fact, nobody has been graded on those reports saying this is wrong. You know, but a lot of the papers have been are kind of disregarded because it says presentation is not appealing. You know, there's no sequence of thoughts, right? Or the model is not built well, or something like that, right? So it's anyway. So we could. People that have good experience with computational tools usually have an edge on this competition. So it's as usual, in real modeling, it's an essential part. So you can take a look at this if you want. Okay. So let me come back to any questions before we start? Any questions about homework that I turned in? Yeah. No, thank you for. So I pushed it back to. Let's see. To next Monday. So there are 3 problems. It shouldn't take you till Monday, but I figured if you need a little bit of extra time. So I'm sorry. So the homework is due Monday. I'll tell you one thing about Chapter 4 and Chapter 5 are pretty much can be read lumped together. So environment, in which your population kind of lives and thrives, and you take into account competition between the same individuals of the same species, then there is simplest model is to introduce a term, quadratic term, that comes from product of x with x, right? And a constant in front of it, meaning that the competition kind of inhibits the growth, right? So the growth rate is decreased at a rate proportional to the square of the population size, right? So again, the higher the population, the faster the bigger the effect, the negative effect on the growth. Okay. Again, this is not the only one, and we'll see other models, but this is considered to be sort of the next simplest from exponential growth. Okay, so this would be just exponential model. All right, and why do we prefer to write it in this form rather than in this form, which is probably, again, more intuitive? The reason we write it in this form is that if you look at the steady states of this population, and we say, what would the population have to be initially so that it stays at that value forever? So that would be a constant solution to this equation. And remember, we said that constant solution means the right-hand side has to be equal to 0. So having it as a product is just convenient. Okay? Because you can see the right-hand side is 0 if x is 0 or if x equals k. Right? So we saw that in the direction field. We saw that zero and k were the 2 steady states. So this is steady state if these 3 problems, I would say if you finish them after Wednesday, maybe we talk more on Wednesday, then you can start working on Chapter 5. And on Wednesday we should start talking about Chapter 5 as well. Right now I left it the same, yeah. Okay, so today I'd like to talk about two examples of dynamical systems. We started talking about last time a little bit, so let me remind you what dynamical systems models are. I just want to copy another. So I have two codes here, two new codes. One talking about a continuous system, and the other talking about a discrete system. So we'll see what the differences are. Okay. Please. Okay, so I'm going to start with talking about, give you an example of a 2D. Well, 1D we saw last time. So it said 1D model would be a logistic model that usually comes from population growth and it says that if I have x as a function of t, it's monitoring the population at time t. Then, let's see, so I'm going to put here in parentheses the rate of change, the growth rate of the population has this expression. So this is Rx plus or minus, excuse me, minus R over K x squared, right? So this is just a constant. Think about it as just a positive constant A, right? So this, every time you build a model, you have to kind of take into account certain effects. In a population growth, there's an intrinsic growth rate, so that's assuming that the bigger the population, the faster it grows, and that applies to I don't know, bacteria population or things that so individuals that don't kind of compete with themselves. It's just kind of unrestricted growth. So this is an intrinsic growth rate. So that's the reason for that is if you only look at that effect, so you ignore every other effect, then what you see here is you see an exponential growth right? And R plays the role of that growth rate. Yeah? So R is the, if you want a sort of a, well, is the ratio between the growth rate and the current population. Okay, so that's called the intrinsic growth rate. But if you have other effects, for instance, if you have a limited optimization tool, and now here are the problems that can be solved with that tool. but nevertheless, I mean, this is not going to exhaust all the possibilities. So I think well, I'm not supposed to comment on this until the competition is over at 6 p.m. But I'll say that the more the more tools and especially if you know partial differential equations, then you can model kind of waves, vibrations, and okay, so the company is called COMAP, and if you look at the contests, it's called MCM, Math Contest in Modeling, and these are the contest problems this year. So, and again, it's still ongoing. So there's one problem of this sweet spot of a baseball. Second problem has to do with some sort of profiling, geographically profiling the location of a criminal based on the crimes that he or she committed. And the last one has to do with this garbage patch in the Pacific. So it's kind of interesting. Usually the description of this kind of interdisciplinary problems take 20 pages. So lots of data, lots of things to look at and try to come up with a model that explains. And I think they also refer to a paper here. So, but what I want to say is that you can look at previous contests here if you're just kind of curious, and you will see lots of, a wide variety. I think last year there was one that had to design a traffic circle, which in the United States is more of a curiosity, right? But